Hi everyone, I am Prasanna Reddy Pulakurti and welcome to our presentation on Shuffle PatchMix Augmentation with confidence margin weighted pseudo-labels for enhanced source-free domain adaptation. This work is in collaboration with DevCom Army Research Lab and Rochester Institute of Technology.
One of the core challenges in machine learning is domain shift. When a model trained on one domain performs poorly when deployed to a different domain. This occurs because data distribution during testing is different from that during training. For instance, a model trained on synthetic data might achieve 99% accuracy, but the same model drops to just 43.8 when tested on real-world data. This discrepancy underscores the need for domain adaptation techniques. Unsupervised domain adaptation, or UDA, tackles this challenge by transferring domain knowledge from labeled source data to unlabeled target data. The goal is to learn a classifier that performs well on target data despite having no target labels. However, UDA methods assume we still have access to the source data during adaptation. This assumption doesn't always hold, leading to the development of source-free domain adaptation techniques. In many real-world scenarios, accessing source data can be difficult or even impossible due to privacy regulations, bandwidth limitations, or security restrictions. Our work addresses this setting, known as source-free domain adaptation, where only a source-trained model and unlabeled target data are available. Here is an overview of our method. Our method begins by generating pseudo-labels for weakly augmented target samples. These labels are produced by passing the image through the encoder and then refining them using nearest neighbor aggregation in the feature space. To address label noise, we propose a confidence margin reweighting strategy that assigns reliability weights to each pseudo-label, helping the model focus more on the confident predictions. Next, we apply our shuffle patch mix augmentation to generate two strongly augmented views of the target image. These augmentations are then classified using weighted classification loss, which incorporates both the pseudo-labels and their associated confidence margin weights. Additionally, we use two losses set forth in reference to the diversity loss and contrastive loss. The diversity loss is introduced to regularize training, and the contrastive loss is introduced to make the two SPM augmentations closer to each other while pushing other samples away. The final model is trained by minimizing the combination of these three losses. Our contributions are in bold. Here is an overview of our contributions. Our first contribution is the confidence margin reweighting strategy. Since pseudo-labels in the target domain can often be noisy, we assign a confidence margin-based weight to each pseudo-label. This weight reflects the reliability of the pseudo-label and is used to reweight the classification loss accordingly. Second, our contribution is Shuffle Patch Mix, a novel intra-image patch mixing strategy that creates diverse and challenging transformations by shuffling and blending patches within the same image. This significantly enriches the target domain data and improves model robustness during adaptation. Here is our confidence margin reweighting strategy. First, let's take a look at the pseudo-label probabilities. If one of the class probability is very high and all the others are low, this means the pseudo-label is very certain and highly reliable. On the other hand, if the probability is low or multiple classes have similar probabilities, then the pseudo-label is uncertain and unreliable. The weighted function multiplies the confidence, which is the top one prediction probability, with the margin, which is the difference between top one and top two prediction probability, by the exponential of margin, as shown in the equation. The exponential term supplies a smooth margin-aware gain that exponentially enlarges the contribution of samples with large margins, whose pseudo-labels are statistically the most trustworthy. Samples with small margins are downweighted so that unreliable predictions exert little influence on the gradients. These weights are incorporated into the classification loss using the presented equation. Starting from the target image, we partition the image into patches and then randomly shuffle them. Later, we sample a random value lambda from a beta distribution and multiply it to each patch. In addition, we multiply the corresponding randomly shuffled patches with 1 minus lambda. The final SPM image is obtained by summing these both results. In addition, standard augmentations are applied to introduce maximum data diversity. Our experiments demonstrate that gradually increasing the mixing strength by decreasing the first value of A of the beta distribution allows the model to better adapt to SPM augmentation distribution. And shuffling patches introduces blocking artifacts. To address this, an overlapping patch blending approach is proposed, where the patches are extracted with larger size than intended and blended linearly with the neighboring patches. This effectively reduces blocking artifacts, resulting in a smoother transition as shown here. As previously mentioned, we optimize a combination of three loss functions following the framework set forth in reference 2. The first is our proposed weighted classification loss, which performs self-training using pseudo-labels while prioritizing reliable pseudo-labels. The next is contrastive loss that makes the two SPM augmentations closer in the feature space while pushing other samples away. The final is the diversity loss that acts as a regularization to prevent the model from collapsing to trivial solution. We benchmark our method on three popular datasets. The PAX dataset contains 7 categories, 4 domains, and nearly 9.9K images, while the DomainNet is a larger dataset with 345 categories, 6 domains, and roughly 586,000 images. The third dataset we benchmark on is the popular VisDA-C dataset, which contains synthetic to real domain adaptation scenario with 280,000 images. We achieve state-of-the-art performance on all major benchmarks. On the single target PAX dataset, we achieve a performance improvement over the baseline add a contrast method by 7.3%, and in the multi-target setting, we achieve an improvement of 7.2%. On the DomainNet dataset, our method outperforms the best SFDA square method by 2.8% and achieves a performance improvement of 3.3% over the add a contrast baseline. On the VisDA-C dataset, our method achieves state-of-the-art performance by outperforming the previous best UPA method by 0.7% and outperforms the baseline add a contrast by 2.6%. In addition, our method achieves best or second best performance in 8 out of the 12 categories. We performed an ablation study to isolate the impact of individual components, and the reweighting strategy improves the performance by effectively handling the pseudo-label noise, and SPM alone can boost the baseline performance by adding diverse and challenging augmentations, while the patch overlap blending offers slight additional gains. Each component helps individually, and the combination achieves the highest averages. Here are the key insights. SPM generates diverse and challenging augmentations and improves SFDA performance. Increasing SPM strength as training progresses leads to better generalization. Our reweighting strategy handles noisy pseudo-labels by prioritizing reliable pseudo-labels. Our approach is particularly effective on small datasets. This is because, firstly, small datasets are prone to overfitting, so SPM is particularly effective in enhancing data diversity. Second, the impact of noisy pseudo-label is more pronounced in smaller datasets, making confidence margin reweighting essential for reducing the influence of uncertain labels while emphasizing confident predictions. To conclude, we introduced the shuffle patch mix augmentation that creates challenging transformation and increases the data diversity. We also introduced a confidence margin reweighting strategy to address noisy pseudo labels. Our approach achieves state-of-the-art performance on three major benchmarks. Future work may apply shuffle patch mix method to other tasks such as object detection and recognition, and also extend it to other paradigms such as semi-supervised learning, unsupervised domain, universal domain adaptation, and video domain adaptation. Thank you for your attention. The open sourced code can be accessed either by scanning the QR code or following the provided link.